Welcome to the fourth video for Chapter 2, in which we look at significant figures in measurements. First, let's look at some important considerations for precision in measurements. First, measurements are different from other numbers. So measurements are like 3.25 centimeters, those other numbers pi, 100 centimeters per meter is a conversion factor, 25 students is a counted number. Measurements represent an action by someone with some measuring instrument. All measurements have a built-in uncertainty, which is the random error that we talked about in the previous video. So no measurement is exact, and this uncertainty is the result of random differences in reading the measuring device. Different people can read differently, and even one person can read differently from one measurement to another. And this amount of uncertainty is the precision, and this depends on how small the divisions or the markings are on the measuring device. A higher precision requires more and smaller divisions, which means that the markings are going to be closer together. Finally, one thing that's very important in this whole class is that all measurements must have units with them. Significant figures are a way to communicate the uncertainty in a measurement. They show the precision to which the measurement was made, basically how precise the equipment was. In order to determine how many significant figures to report in a measurement, you read to the smallest division of the device. These are then the certain digits. And then because the eye is very good at estimating, you're going to estimate one more digit between the last two certain, or after the last certain digit between the last two smallest divisions that you have. For electronic equipment, such as our balances, the last digit is electronically estimated, and often you'll see it fluctuating or varying up and down, and you'll ask in class which value to use, and I'll tell you just pick one. It doesn't matter. That's because that is just an estimate. So let's take a look at what I mean by looking at this ruler measuring the length of a pencil. This first ruler is marked to 10 centimeter divisions, which means it reads to 10 centimeters. Because of that, we have to estimate to the ones place that last significant figure. So if we drop a line here, we'll see that we can estimate somewhere between, well, we know that the pencil is between 0 and 10 centimeters. That's the best that we can say for certain. We're going to estimate that last significant figure as 9, and so the 9 centimeters becomes our reported measurement, and in this we see one digit. That's a single significant digit. If we increase the number of markings, that means we decrease the size of the divisions, so we've now have this ruler marked off to 1 centimeter divisions, so we can read actually and be certain of the centimeter length, so we can be certain of the 9 here. Now we have to estimate to the 10th of a centimeter, and I'm going to estimate in this case 0.4 as the location of the end of that pencil for a reading of 9.4 centimeters. In this case, you see that we have our certain 9, our estimated 4 for two significant figures in this particular pencil. Reasonable people might have said 9.3, and somebody might have said 9.5. Anywhere between 9.3 and 9.5 is a reasonable estimate. If we then increase the number of markings one more time, now we have 10th of a centimeter divisions marked off, and we have to estimate to the 100th place. So in this case, we know the 9 for certain, we know the 0.4 for certain, so they become our certain digits, and we're going to estimate between the 0.4 and the 0.5 where that line ends up. I'm going to say it looks like 0.03, and so I have a reading of 9.43 centimeters. The two certain digits and the one estimated digit give me 3 significant figures. As before, you can be off by 1 in this last digit, so anywhere between a 9.42 and a 9.44 would be considered reasonable estimates of this length. So as you can see, as the size of the divisions decreases, we went from 10 to 1 to 0.1 centimeters, the precision of the measurement and the number of significant figures, or sig figs, is going to increase. So let's practice making readings using this ruler, marked off in centimeters. I want you to estimate the distance of each of those arrows along the ruler from A to E to the correct number of significant figures. I'm going to pause the video now, make your estimates, and we'll come back. Alright, so we're back. Here is the first reading, 0.50 centimeters for A. You notice that 0 tells me that I think that the marking is right on that 0.5. It's not a little to the right, it's not a little to the left. Reasonable estimates would have been 0.49 to 0.51 centimeters. Anything in between those two would be fine. For B, I'm saying 3.28 centimeters. I know the 3 for certain. I know the 0.2 for certain. In between there, where is that B? I'm estimating 3.28. Anywhere between 3.27 and 3.29 is probably a very reasonable estimate for those as well. For C, well, C looks like it's right on the 5.5 mark. So because it's right on that mark, and because we have markings to the 10th of a centimeter, we have to estimate that last digit. And so this is going to be a 5.50 reading, 3 significant figures. Anywhere between 0.49 and 0.51 is also an appropriate reading. 7 is a little bit tricky. Let's look at this one before we show you the answer. This 7 really is 7.0. It's telling me that this number is not only 7, but it's the 0.0 mark for the 7, because this is 0.1, this is 0.2. If I want to indicate that that arrow is right on the 7.0 mark, then what I have to report is 7.00 centimeters, indicating that both of these zeros are made from this measurement and are indicating that I'm right on the 7.0 mark. Finally, this last one, if you look closely, E looks like it's just to the left of the 8, which is for certain. Now, since it's to the left of the 0.3, that means 0.2 is the next digit, and right to the left of that, just to the left of that, would be 8.29 centimeters. Anywhere between 0.28 and 0.30 is probably a reasonable estimate as well. Alright, suppose you have a reading that you're looking at and you want to determine how many significant figures there are. There are some rules we have to recognize the number of significant figures that are reported in a measurement. First, all non-zero digits and any zeros between them are significant. Now you're going to find us focusing in on the zeros because they're the ones that are going to be the hardest thing to know for sure. It makes sense that all non-zero digits are going to be significant. And any zeros in between them, well, you're going to see it's going to start to make sense that having, if you're surrounded by significant figures, then they must be significant. Now to us, what does significant mean? Significant means that this is part of the measurement. So we're going to assume that all these numbers represent measurements, and the number of significant figures in them is given by the number of figures that are between the non-zero digits, or if there are only non-zero digits, then that would be the number of significant figures. Because the 5 and the 4 is significant, the 0 must also be, so this is 3 significant figures, or sig figs. All 5 of these digits are significant, including the 0 that's in between the 4 and the 1. Because there's a 2 on one end and a 2 on the other end, those are non-zero, they're significant, so the 4 zeros in between are also significant, so this is going to be 6 sig figs. And again, 4 digits, all of them here are significant. So how do we tell when zeros are or are not significant? And what does it mean when they're not significant? So if a decimal point is present, then the largest magnitude or largest place of the non-zero digit is going to be considered the most significant figure. Any digits to its right are considered significant. They're considered to be part of the precision of the measurement. So sig figs, I want you to really get this internalized. Sig figs are really indicating the precision of the measurement. Any zeros to the left of that first or largest non-zero digit are just going to be magnitude zeros. They're going to be used to maintain the correct size of the number. They are important to the value because they maintain the magnitude or size of the number, but they are not considered part of the measurement, part of the precision. Alright, let's look at these four numbers here. The zeros in front of the first non-zero digit are the placeholders. These are the magnitude zeros, indicating that the 2 should be in the thousandth place and not in the hundredth or the 10th place or anywhere else. So it's our first significant figure. It's the largest non-zero digit. The 3 is the only other non-zero digit that follows, or only other digit that follows it. So in this case we have two significant figures. Here the 9 is our first non-zero digit. Every digit, including that included 0 afterwards, counts. We have three significant figures here. The zeros ahead of time, they don't count. Think of it this way. If we covered up the 9 and the 0 and the 1 here, there are no significant figures in here, so they don't count at all. In this third number, we have 1, a single non-zero digit to start with, so we only have one sig fig. And finally, in this third number, we have 3 non-zero digits, or 3 digits that follow that first non-zero digit, and so we have 3 significant figures. If you have zeros after the last non-zero digit and you have that decimal point present, we still have a decimal point here, then those zeros are going to be significant. They are going to be measurement zeros. One of the ways you can think about it is that if you were to add another 0 after that 0, it would not change the size of the number. So there's a reason why that 0 is there. It's made to show what the precision of the measurement was. So for instance, if we look at these four numbers, let's look at the 25.0 for example. If we put a 0 there, it's not going to change the size of the number, which means that that first 0 there must be significant. Here's our first non-zero digit, our second. Everything that comes after that first non-zero digit is significant. And so we have 3 sig figs here. In this case, the same thing. The 0 here is in between two non-zero digits. The first non-zero digit is 3. 4, 0, 2, 0 gives us 5 significant digits. In this case, this is really tricky. These first 4 zeros are not significant. They are the magnitude, or the placeholders. This 6 is our first non-zero digit, and every digit after that counts as significant. We have 4 significant figures. In this case, there's a reason why I have the decimal point here, even though there's nothing after it. If I didn't have a decimal point, as we'll see on the next page, we wouldn't consider these zeros significant, but because that decimal point is there, here's our first non-zero digit, and every digit after that counts as being significant, and that's the way to make numbers like this one have zeros that are significant. This is 3 significant figures. Continuing, if there is no decimal point, then any zeros after the last non-zero digit are only going to be magnitude zeros. Because the way to think about this is if you added another 0, it would change the size of the number. That means that it's only there as a placeholder or a magnitude. In these examples, if I put a 0 after 70, it makes it 700, and so that 0 is only there as a placeholder to tell me that that 7 is in the tens place. We have only one significant figure, the 7. In this case, these 3 zeros are not significant. Here's our 1, and here's our 2 is our last non-zero digit. It's that last non-zero digit that's going to stop us, and so we have 2 significant figures. In this case, the 1 is our last non-zero digit, so the 8 and the 0 and the 1 count, but not the zeros after it. Finally, in this last one, the 9 is our last non-zero digit, so everything between the 2 and the 9 is significant, and we have 5 significant figures here. Scientific notation makes things really easy. In scientific notation, all digits in the coefficient only. We're going to ignore the exponent, but all digits in the coefficient are going to be considered significant, and you'll see there is a decimal point, so it's going to help us make sense of it. In these numbers, we have two significant figures in the first one. We have 4 in the second one because there are 4 digits. There's a decimal point present, so everything after that first non-zero digit counts. In this third number, we have a 4 followed by 4 zeros, so we have all of those numbers counting, 5 significant figures. And finally, in the last number, we have 3 significant figures. You notice the size of the exponent makes absolutely no difference. It makes absolutely no effect on the number of significant figures. Finally, there's a set of numbers that have infinite or unlimited significant figures. These infinite and unlimited significant figures are counted numbers, so if you can count something, or a defined number, conversion factors, or standard values, those are going to be significant figures. For instance, 12 eggs is a count. You can't have 12.1 eggs. You can't have 11.9 eggs. If you accidentally count 13, that's a mistake. That's not random error. That's a mistake in your measurement, so that doesn't count as counting towards precision. 100 pencils. Again, you can't have 99.9 pencils. You can't have 100.1 pencils. You have 100 pencils, and if your count is correct, then that's fine. Also, money. $1,200. You can count money, so you can be certain that you have the correct amount of money. Conversion factors as well are exact numbers. It's always 12 inches per foot. It's never 13. It's never 11. You can't have 12.1. You can't have 11.9. It's always 12, so this is an exact number. For 1,000 milligrams per gram, this is a defined conversion factor. It's exact. There's never going to be 1,000.1 milligrams per gram. There's never going to be 1,001 or 1,100 or any other number other than 1,000 milligrams per gram. Likewise, 16 ounces per pound, never 15.9, never 17, always 16 ounces per pound. Alright, now I want you to go ahead and practice significant figures. Look at the values below, determine how many significant figures there are, and I'm going to pause the video and then come back when you're ready. Alright, so you've resumed the video, so hopefully you're ready to go. Let's take a look at the significant figures. In the first value, we have 2 significant figures. There's no decimal point present. So since there's no decimal point present, that means that the 0 is only a magnitude 0. I'm going to indicate that by putting an M in that circle for a magnitude 0. We have those 2 significant figures. Likewise, in the second value, those leading zeros are magnitude zeros. If I put another 0 in there, it would change the value, right? That first non-zero digit tells me I've got 1 significant figure. In this third number, there are no zeros, so it's pretty unambiguous, 3 significant figures. In this fourth number, that 0 is included, so because that 0 is included, I get 5 significant figures. In this number, these zeros are magnitude zeros, and so I've got 2 significant figures, the 4 and the 5. Forks, you can count forks, so that's an unlimited number of significant figures, or infinite. 4,000 kilometers, that's a measurement. Kilometers is a measurement, so I have 1 significant figure. That's my last non-zero digit. There's no decimal point, so these are magnitude zeros. Scientific notation tells me that everything in my coefficient is significant, so I have 2 significant figures. Centigrams per gram is a conversion factor. It's an exact number, so it's infinite. And finally, another scientific notation measurement. I'm sorry about that. So everything in the coefficient is significant, and we have 3 significant figures. Alright, so in class the next day we are going to be looking at practicing what we've learned in this and the previous video. Please, if you have any questions, go back and review this video and the previous video. I'll see you in class.